This video is about nucleophilic substitution. There's two types of nucleophilic substitution. One is the SN2 and the other one is SN1. We're going to see both in this video. But first, we're going to understand what's homolytic and what's heterolytic fission first. Okay, you might have already learned the free radical substitution, whereby you see chlorine in UV light. The homolytic fission is going to happen. What does that mean? It means that there's a bond breaking here, whereby the electrons are broken, the bonds are broken and the electrons are spread evenly, one to each side of the chlorine. So we'll get two identical chlorines. That is a radical. The radical here actually means that odd electron here. That is a homolytic fission. We break the bond evenly. A heterolytic fission, on the other hand, is going to form a positive charge and a negative charge. So if I'm going to draw the same chlorine again, so I'm just using the same example, chlorine. For a heterolytic fission, it's going to break not so evenly. So this chlorine is going to be negatively charged and this chlorine is going to be positively charged. So we're not going to get two of the same thing. Instead, we're going to get a Cl plus and a Cl negative. So this is a heterolytic fission. The focus of this video would be the nucleophilic substitution mechanism. But if you know how to draw one, you would know how to draw all of this because they all look the same. And RF, or a halogenoalkane that has a fluoro, would be the slowest compared to RCl, and that would be slower than RBr and slower than R iodide. This is because RF is the shortest, the bond is the shortest, so it's the strongest. That is why the rate of reaction would be the slowest. Do revise what is primary, secondary, and tertiary halogenoalkanes, and how do you see how it is primary, secondary, or tertiary. And for this mechanism, SN2, or nucleophilic substitution with its second order, happens for primary and secondary, while tertiary halogenoalkanes undergo SN1, which is nucleophilic substitution of first order. Okay, those order are the same order that you learned in reaction kinetics, that's the order of reaction. So it's related to rate equals to K halogenoalkane and one of these. Or it could be halogenoalkane and OH, any one of those. So that is why second order, and that's why the 2 here. Whereas for tertiary halogenoalkanes, the rate is equal to K halogenoalkane. You don't see the OH or the CN here, which is why this is a first order reaction. That's why nucleophilic substitution first order. We're going to use 1-chloropropane as our example, but I'm going to draw it in tetrahedral shape. So if I were to draw that in tetrahedral shape, focusing on this carbon, I'm going to get something like this. So Cl, H, H, and the ethyl group is here. Okay, what's going to happen is, say the OH comes in, the OH comes from an NaOH or a KOH. So Cl is slightly negative and the carbon is slightly positive, which means the OH as a nucleophile, something that loves electron diffusion sites, will love this carbon because it's delta plus here. So it's going to go close to that carbon here and form a transition state here, which is negatively charged because this was neutral and the OH is negatively charged. So obviously our transition state would be also negatively charged. So when these electrons move towards the carbon, these electrons will move towards the chlorine. So that's how it got detached. It's a heterolytic fission. So the Cl breaks and therefore you'll form an alcohol. So you're gonna get propan 1-ol. Okay, to make it clearer of how this nucleophilic substitution happened, I'm gonna draw it in this way so that you can see that the product is in its mirror image. So I'm going to put a star on one of the hydrogen so that you have 4 different items here. It's CH2, CH3, a Cl, a H, and a H with a star. I just want to mark it so that you can see that you're going to get a mirror image of what you had in the beginning. Okay, so the same thing happens. The OH, same as the one at the top. The one that I showed before is with less details. So the OH goes in because this is delta plus and this is delta negative. It forms this transition state. Or we can call it the activated complex. Okay, remember that if you have 4 bonds, 4 bond pairs, the shape is tetrahedral, so you need to revise that by now, BSDPR. And if you have 5 bond pairs, it's going to be the trigonal bipyramidal shape. So that's what it is right now. This is the triangle shape, and this is the one that is 90 degrees from it. Now, when I draw the product, it's going to be the mirror image of what we had as the reactant here. So the OH goes to the other side. And the H with the star is here now. So it got pushed, like sort of pushed to the other side. And the OH just goes here. So all of them are going to be this orientation, which is the mirror image of the reactant. Before going through the SN1 reaction, let's look at what I drew here. This is to demonstrate the positive inductive effect of R groups, alkyl groups. So alkyl groups, they will sort of push electrons to stabilize this positive charge. But if you have 3 of them, then it will push, push, push and stabilize this very much. So this is the most stable carbocation. This is second because there's 2 R groups to stabilize that positive charge. And this is the least stable, which is why primary halogenoalkanes don't undergo SN1, but tertiary halogenoalkanes, their intermediates are very stable. The carbocations are stable because of the R groups that's electron releasing and pushing the electrons to stabilize this positive charge. This is why SN1 happens for tertiary halogenoalkanes, but not the primary and secondary. So primary and secondary will undergo SN2 as how you saw it just now. Okay, now on purpose, I'm going to show you a tertiary example that has a chiral carbon. Chiral carbon attached to 4 different groups or atoms. So this is a methyl, ethyl, propyl, and bromo. So all 4 are different here. This is a chiral carbon. Okay, I'll show you the simple one first, then I'll show you in 3D. So since this intermediate is stable, so what's going to happen is the electrons will move towards the Br and make a carbocation. So this is going to be a CH2, CH2, CH3. That's the propyl, ethyl, methyl. And the Br just comes right off. This happens slowly, and this is the intermediate. This has an intermediate, unlike the SN2. It doesn't have an intermediate, remember? And so that carbocation then reacts with the OH. If you recall the reaction kinetics chapter, you'll recall that anything that appears in the fast step does not appear in the rate equation. So this is why it's first order. That's why SN1. That's what that 1 means, the order of reaction. So what happens here is the OH negative and the carbocation, they bond with each other. Now, overall, if you look at the SN2 and SN1, the reaction is actually the same. The OH went in and the halogen came out. So OH goes in and end up here, and the halogen comes out as a negative charge. SN1, same thing. The OH goes in and the halogen comes out. So overall, they are the same, but the mechanism is different. So if we were to write an equation, they would look like the same reaction. But if we write the mechanism, we'll see that SN1 and SN2 is not the same thing. SN1 has an intermediate. Okay, let's put it in the tetrahedral way. So I put it in tetrahedral form. You can put it anywhere you like because the positions are all identical. They're all 109.5. So I'm just going to put the Br on that side. And I put CH2, CH2, CH3 on top because there's more space to draw that long alkyl group. Okay, so what happens in the first step, the slow step, is that the Br is going to detach. It's going to break. Heterolytic fission there. Let me erase the angle here. And what's going to happen is it's going to form something that is 3 bond pairs means it's going to be trigonal planar. So the intermediate here is trigonal planar. So I'm going to draw that. Now, can you please imagine this, that it is flat trigonal planar like that? It's this way going into our page so that I can demonstrate to you what's going to happen next. So the Br came out. Same as what happened up there. And I'm going to redraw this down here as the first step. Now, if we compare it with the SN2, this shape was fixed because the OH will definitely go on the opposite side. It will definitely enter the halogenoalkane on the opposite side as the chloro. So we have 100% of the same thing because this transition state is trigonal bipyramidal. So we'll definitely get that mirror image from the reactants. Okay, but for this one, since it's a trigonal planar, this is a trigonal planar intermediate. So if it's a plane, the OH can enter from this side or this side. It's random. There's a 50% chance that it'll enter from this side and a 50% chance that it'll come from the other side, which is why I'm gonna get both the mirror products. I'm gonna draw that. So if the OH came this side, the OH comes here, and the CH3 will be here, and CH2, CH3 will be on that side. If the OH comes from the other side, so it will end up here, and the CH3 will push to the other side here, and this will be pushed to the other side, so CH2, CH3. If you haven't noticed, this a mirror image of each other. A 50-50 mixture of these mirror image organic compounds. It's called a racemic mixture, which you will learn under stereoisomerism. If we were to compare the rate of reaction of the halogenoalkanes, for those halogens that are leaving the group, if they were iodide, then it'll be the fastest because a C to an I has the longest bond. So it's easiest to break this. So then this part will happen much easier. Same goes for this one, SN2. The breakage of a CI would be the easiest. Therefore, it's the fastest in its rate of reaction. A bromoalkane will be second, and chloroalkane the slowest. A fluoro don't usually react, or it's very, very slow. So you'll see that in exams, most of the time it's iodo, bromo, and chloro. Chloro being the slowest. The rate of reaction also depends on whether the halogenoalkane is primary, secondary, or tertiary. So if it's tertiary, it's the fastest, and primary is the slowest. Okay, the rate of reaction will also depend on the choice of solvent. Protic solvents mean that they can form hydrogen bonding, and aprotic solvent means they don't form hydrogen bonding. So like, for example, dichloromethane, that means dichloromethane. So it's polar, but there's no hydrogen bonding that can be formed in this dichloromethane. So that's what aprotic means. There's no hydrogen bonding formed. And protic solvents are like water or alcohols, can form hydrogen bonding. Polar aprotic solvents are better for SN2 reactions. So you can speed up the reaction by using aprotic solvents because there's no hydrogen bond. If there's hydrogen bond, it will hinder it from attacking the carbon with the leaving group, which is the chloro or the bromo. So having hydrogen bond is not favorable for an SN2 reaction. So most of the time we will be using aprotic solvents for SN2 reactions.